you all to this special lecture, which is the Vainu Bappu Memorial Lecture. And this is given by Professor Sreenivasan. And to give a little background of the Institute as well as Professor Vainu Bappu, the Institute has origins as early as 1786 when an observatory was set up in Chennai, and it began functioning in 1792 in Nugambakam. And then the observatory moved to Kodaikanal, and it was called as the Observatory Kodaikanal. And in 1971, the observatory became an autonomous body under the name Indian Institute of Astrophysics. And this transition was done none other than Professor Vainu Bappu, and therefore Professor Vainu Bappu was considered as our founding director. And the headquarters of this institute moved from Kodaikanal to Bangalore in 1975. So 2020-2021 is our Golden Jubilee year, and we are celebrating with a number of conferences, meetings, and events. And this conference is also dedicated to the commemoration of the 50th year of the Institute. The Institute comes under the governance of Ministry of Science and Technology and is ably guided and supported by the Department of Science and Technology. And incidentally, the Department of Science and Technology is also celebrating its Golden Jubilee year. So this event is under both IA 50 and DST 50. And thanks to the vision of Professor Vainu Bappu, we have grown since the Kodaikanal days. And through his vision, we set up the observatory in Kavalur, where initially a 1 meter telescope was set up, and then a 2.34 meter telescope was set up indigenously. We also set up a radio observatory in Gauribidanur. Then we wanted to have the night sky was getting polluted, etc. in the southern, and also because of climate change, the clear nights were getting reduced. We went on an expedition to set up an observatory in the Himalayas. In late 1990s, we set up one in Hanle, and the 2 meter telescope was installed there. And that 2 meter telescope has completed now 20 years of its operation at an altitude of 4,500 meters above sea level. The observatory in Hanle is functioning well, and then the observers do not go to the site for taking data. They go to a campus in Hosokote called the CREST campus, and it is remotely operated from this campus. We also have set up an MGK and Space Sciences lab in the CREST campus, and that lab delivered the UV imaging telescope on AstroSat. And AstroSat was launched in 2015, and it has completed 5 years of operation in orbit. And the payload operation center of UVIT is located in the Bangalore Korubangla campus. And now we are embarking on future journeys. The VLC on Aditya is getting integrated in the MGK and Space Sciences lab. We are also embarking on setting up of a national large solar telescope on the banks of Pangong, the Merak site, and many more projects up in the anvil. So I'm happy to say that the vision of Professor Bappu is carried forward, and we look forward to many more achievements and milestones in the next half of the century to come. I now request Professor Vinod Kishan to introduce the speaker and also read out the citation. Professor Vinod Kishan.
Thank you. Thank you, Annapurni. Okay, I'm unmuted. Okay, thank you very much. And
yeah, we can hear you. Go ahead.
Pardon?
We can hear you. Go ahead.
Yeah. Okay, good. Okay, so namaskar, everyone. This greeting is valid throughout the day. So namaskar, and special namaskar to Professor Sreenivasan. So it is indeed a great honor and an honest pleasure to introduce Professor Sreenivasan on the occasion of his receiving the 10th Vainu Bappu Lecture Award. I call it award. Professor Sreenivasan holds several prestigious positions. He is the Kleiner Professor and the University Professor at the New York University. He has joint appointments at the Tandon School of Engineering, and the Courant Institute of Mathematical Sciences. Professor Sreenivasan served as the director of the Abdus Salam International Center for Theoretical Physics for several years, for nearly 7 years, while still retaining his professorship at the University of Maryland. It is during this period that we held the first Kodai Trieste workshop on astrophysical plasmas with major support from the ICTP. But let me begin from the beginning. After completing his schooling in and around the town of Kolar, Professor Sreenivasan joined the University Visvesvaraya College of Engineering, where he got his undergraduate degree in mechanical engineering. Perhaps this is where his tendency to outdo himself began to be noticed, and then came the Sir M. Visvesvaraya Award for Excellence in Undergraduate Education. Inspired and infused by the sagacity of role models such as Adi Shankaracharya, Vidya Aranya, and Vivekananda, the young Sreenivasan ventured into the world of scientific inquiry. Intense desire to see science in action propelled him to choose subjects such as aerodynamics and fluid dynamics instead of, say, particle physics, according to him. Under the guidance of Professor Rodam Narasimha at the Indian Institute of Science, Bangalore, he started with theoretical work and then immediately set up experiments to validate his theory. This was the work on the relaminarization. It's really a mouthful, Srini. This was the work on the relaminarization of a turbulent fluid, that is from laminar to turbulent and back to laminar. Though controversial at the time, the theory and the experiments have stood the test of time. Fame followed in the form of the Best Thesis Award of the Indian Institute of Science. One of his first postdoctoral assignments at the universities of Sydney and Newcastle was to study the interaction between the atmosphere and the ocean. The measurements of the various fluxes, such as mass, momentum, and heat, were carried out in the sea between mainland Australia and Tasmania. The experience thus gained from field measurements came handy while measuring heat flux during the solar eclipse, which happened around the same time. After Australia, the play field shifted to the US, where Professor Sreenivasan joined the Johns Hopkins University and interacted there with the legendary fluid dynamicist Stanley Coursin, whom he described as his academic grandfather. In the exalted company of these luminaries, he realized that with the appropriate diligence, one could also grow to emulate them. That's a very nice lesson. Then Yale University happened, just for the asking. Beginning with the position of assistant professor, Professor Sreenivasan was soon after appointed as a full professor in the departments of physics, engineering, and mathematics. Here, nonlinear dynamics and chaos were the areas of his interest. In particular, experimental investigation of the interface between a laminar and a turbulent flow to see if it had the properties of a fractal. Success encouraged him to continue the study to multifractals and questions of universality. More recently, it has been shown that the inclusion of circulation brought in a simplification whereby the phase space filling characteristics of the high and the low order moments can be easily identified. The awareness of the needs of the US Navy brought to his attention the importance of full-scale modeling and on-site testing of the submarines in the lakes of Idaho. Professor Sreenivasan at this time became keenly interested in using a fluid of extremely low viscosity, such as the superfluid state of helium, and thus forayed into the realm of quantum turbulence. Visualization of the quantized vortices and study of their mutual interactions and connections broke fresh grounds in the area. A study at the highest ever Rayleigh number of 10 raised to power 17 has been reported in his landmark paper on convection. This has led to a novel understanding of the solar magnetic activity, the butterfly diagram, and related phenomena. This is also the topic of today's lecture. Awards and honors started pouring in early in Professor Sreenivasan's scientific career, with several prestigious fellowships, just to name a few, such as the Humboldt, the Guggenheim, the Third World Academy of Sciences, the US National Academy of Sciences, and positions such as the Centennial Professor of the Indian Institute of Science and the C.V. Raman Professor of the Indian Academy of Sciences. Medals such as the UNESCO and the Dwight Nicholson and the National Order of Scientific Merit of the Brazilian government. The list continues. With this rigorous and highly prolific scientific journey, one may imagine Professor Sreenivasan to be a person of reserve and rather fiercely protective of his time and space. But he strongly believes in maintaining a healthy life-work balance. No wonder we always see him with that transcendent, luminous smile. Can we have the smile? At this bright note, I stop. Thank you, Annapurni. Shall I read the citation?
Yeah, please read out the citation, please.
Okay. So this is the citation. Professor Kattepalli R. Sreenivasan, Fellow of the American Academy of Arts and Sciences, the National Academy of Sciences of the USA, the Indian Academy of Sciences, and the Eugene Kleiner Professor for Innovation in Mechanical Engineering at New York University, while also holding the university professorship. A rare honor is a distinguished scientist who has made fundamental contributions in the fields of fluid convection and turbulence. He has appointments in the Tandon School of Engineering, Graduate School of Arts and Sciences at NYU, and the Courant Institute of Mathematical Sciences. He served as the director of the Abdes International Center for Theoretical Physics for nearly 7 years. The underlying theme of Professor Sreenivasan's scientific research has been the study of laminar and turbulent fluid flows from quantum to stellar scales. His early work on the relaminarization of a turbulent flow created quite a sensation among the thermodynamicists, worrying needlessly about the fate of the second law of thermodynamics. His work at the universities of Sydney and Newcastle on measurements at air, sea, and land-sea interfaces led to major developments in the understanding of mass, momentum, and heat transport, which later also deepened our understanding of the mechanism of heat transfer during the near total solar eclipse. Professor Sreenivasan's work helped the US Navy realize the importance of carrying out full-scale modeling on-site in the lakes of Idaho to understand the drag on the submarines. He gradually turned his attention to more and more fundamental parts of his science, addressing questions of profound interest in statistical physics, critical phenomena, and non-equilibrium flow systems. Since turbulent flows come in all ranges of Rayleigh and Prandtl numbers, Professor Sreenivasan fulfilled the need for a large Rayleigh number by commissioning helium as a fluid which brought in the realm of quantum turbulence. The one range that is not easy to create in a laboratory exists in the solar convection zone. And that's what attracted Professor Sreenivasan to explore the nature of solar convective turbulence. The exploration goes on. The showers that started with the Sir M. Vishwesvaraya Award for Excellence in Undergraduate Education built up into a storm of laurels as Professor Sreenivasan's research achievements continued to dazzle the scientific community. With several prestigious fellowships such as the Humboldt, the Guggenheim, the Third World Academy of Sciences, the US National Academy of Sciences. Positions such as the Centennial Professor of the Indian Institute of Science and the C.V. Raman Professor of the Indian Academy of Sciences. Medals such as the UNESCO and the Dwight Nicholson and the National Order of Scientific Merit of the Brazilian government. The list continues. It is indeed a great honor and privilege for the Indian Institute of Astrophysics to confer the 10th Vainu Bappu Lecture Award on Professor Pathipalli R. Sreenivasan. Thank you. Back to you, Annapurni.
Rajguru, tell me when I should start.
Yeah, Professor Sreenivasan, yeah, we're very happy you're here. And I mean, unfortunately, we're not able to give this to you personally, but definitely we look forward to you amongst us very soon. So please start your lecture.
Thank you very much. Let me share my screen somehow. Okay, you should be able to see my screen.
Yeah, it's
Can you
now.
confirm? Yeah, okay, thank you.
Yeah, yeah. Yeah, we can hear
thank
you. Yeah.
Thank you, Vinod, for your kind and extraordinarily generous introduction. I'm surprised that so much information about me exists somewhere on the web. I'm actually very embarrassed by your kindness. And in any case, it's good to see you, albeit 10 years or so later, and to discover that you have not changed at all. Congratulations. I'm very grateful to Director Annapurni Subramanian and to Professor S.P. Rajguru for this invitation to deliver the 10th Vainu Bappu lecture. Rajguru kindly listed for me the previous 9 Bappu lectures, and I am truly honored to belong to that group by being the 10th. You no doubt know that a number of distinguished physicists, mainly astronomers and cosmologists, have speculated that our universe is fine-tuned in some sense for life. For example, if only the physical constants such as the coupling constant of the strong force were to have been different by a very small amount, our universe would not exist. I cannot be certain about such speculations, however well informed they are, but I will say this. If we didn't have atmospheric convection, for instance, there would be no winds, no clouds, no rain on land, no crops, and nothing that would sustain human life. Likewise, if there were no convection in the Earth's core, there would be no magnetic field, no geodynamo, and the Earth's atmosphere would have been much like that of Mars, unable to support life. If there were no convection inside the sun, the high energy particles would directly impinge the Earth or whatever is left of the atmosphere to destroy it. No matter how one looks at the problem, convection as a phenomenon appears very closely linked to the existence and survival of human life, which is partly why I chose to speak about it today. with the hope of making a reference to the convection processes in the sun, which is a subject of great interest to all of you at the Institute. I added a qualifier to the title, mostly because what I will say about convection in the sun borders more on similes and metaphors rather than directly on the real thing. And nobody has been able to solve the convection problem in the sun in all its glory, certainly not me, despite some valiant efforts. An alternative title for my talk could have been this: How turbulent is the sun? This is a question that I would like to answer more definitively some other time, but we'll only be hinting at this today. I'm particularly pleased that this lecture happens to be coinciding with the 10th anniversary celebrations of the Indian Institute of Astrophysics, and also DST, and also other anniversaries as well. From this picture, which I stole from the website of the Institute, IIA's history can be traced back to 235 years, as Annapurni already said. But its present structure was created by Vainu Bappu, whose picture I show here. By the time he met his untimely death in 1982, at the age of 55, he had already become a larger-than-life figure in Indian astronomy and astrophysics. I had never met him. I had just begun my research studies when he already became the IIA director. So after these many years, your kind invitation motivated me to acquaint myself with his person and science. I particularly liked, for example, this obituary by Kocha and Menon, which I think you should read if you haven't read it already. And I took a statement from the last lecture he's supposed to have given in Ahmedabad. It's better to live for a moment in the brilliant sunlight of victory or die in the dark midnight of defeat, rather than to live forever in the dim twilight which knows neither victory nor defeat. I think taking a good look at his life overall, this is a befitting statement of his philosophy. I'll say more about Vainu Bappu towards the end. My long-lasting interest here is to explain these two observations, which began with my work with Shravan Hanasoge at the TAFR. The first one is the so-called anomalously weak convection, which Shravan, Tom Duval, and myself wrote about in 2012, basically saying that the velocities in the convection layers observed by helioseismology methods were far weaker than expected by, let's say, mixing length arguments. These estimates and others have been examined lately by Aaron Birsch and also Laurent Guizan, who more or less have confirmed the conclusion. So this is a spectrum of the energy as a function of the angular degree. And if you integrate that, you will find that the magnitude of the velocity in the convection region is about 1 or 2 orders of more than 1 order of magnitude smaller than what you might expect from mixing length estimates. The second conundrum, which is shown on the figures on the right, about which Shravan may choose to speak later, is that when you look at the spectral distribution of the velocity, which is what you have here, magnitude on the vertical axis and the something like a wave number on the horizontal axis, you will see that compared with the state-of-the-art simulations shown by full lines, the seismology measurements shown by the shaded lines, they differ a lot, and there's a depletion of energy in the large scales, that is low wave numbers. You can see this difference very conspicuously, and this is something that we need to understand. So these are my excuses for actually trying to learn a little bit more about the sun. As I said, nobody can compute the sun in full glory to explain all this unambiguously. So what I will do is solve a paradigm problem under a variety of parameters that approach the suns in some sense or another. And I use, as I said before, similes and metaphors to learn a little bit more about these two issues and also about others if time permits. And the trade-off is that I can obtain some relatively precise answers for a very simplified problem whose conclusions may apply to a wide range of real situations, but only qualitatively. The paradigm problem is the so-called Rayleigh-Benard convection, which you all know very well, but I will describe it just the same as a reminder. We consider a container of height h and the horizontal dimension d, which houses a fluid whose isobaric expansion coefficient is alpha, kinematic viscosity is nu, and the thermal diffusivity is kappa. And we maintain the bottom plate temperature to be delta T larger than the top plate temperature by heating the bottom plate and cooling the top plate. All the energy injected into the bottom plate goes through the fluid to the top plate, and this is what really sets the motion of the fluid. As we know very well, if the temperature is very small, the temperature difference is very small, the heat transport is really by conduction and the temperature profile is linear. We know this from, well, I learned it soon after my high school. If the temperature difference becomes larger, a point will be reached when conduction alone is unable to accomplish the needed heat transport. So the fluid starts moving, thus transporting the hot fluid of low density from the bottom plate to the top and vice versa. This is convection. When the temperature difference is modest, in the sense to be made more precise very soon, the resulting convective motion is very regular, perhaps even periodic. Our interest here is when the temperature difference is very large, when the motion is turbulent. One question to answer is, if I fix the temperature difference delta T between the bottom and top plates, how much heat is transported across the fluid layer? Other questions concern the nature of the fluid motion, the structure of the temperature field, etc., all of which are turbulent as well. As everyone knows, the temperature difference is measured in terms of the so-called Rayleigh number, which I have defined here. The temperature difference delta T is in the numerator, and G is the acceleration due to gravity, and everything else has already been defined. And this number falls from the equations of motion directly. And the other parameter that appears, as Vinod already mentioned, is the Prandtl number, which is the ratio of the two diffusivities, the kinematic viscosity to thermal diffusivity. And what one is after is to, as I said, the heat transport, which is measured in efficiency of the convective motion in transporting heat. So I've defined it already. And the question that I asked earlier, how much heat is transported for a given delta T, can be asked in these non-dimensional numbers. What is nu, that is the nu, Nusselt number, as a function of the Rayleigh number, Ra, and the Prandtl number, Pr. Now, other aspects that will enter the picture and will alter the heat transport, I've listed them all here. Aspect ratio, which is the ratio of the horizontal dimension to vertical dimension, geometry effects, rotation, which is measured through Rossby number, variable properties, flow structure, etc., all of which I have considered, but I only talk about some of them very briefly. And like to draw a qualitative conclusion about the convection in the sun, which is shown the very right, and maybe the Earth, but probably we don't have time for that. To show the extent of the work in which I've been involved, I plot on this diagram. On the horizontal axis is the Rayleigh number, logarithm to base 10. So here it goes from 10 to the power 5 to 10 to the power 17 or something like that. And on the vertical axis is the logarithm of the Prandtl number, going from 10 to the power minus 3 to 10 to the power 3. And the experiments we did, as Vinod already mentioned, using cryogenic helium with the authors whose names are mentioned in the green oval to the left, covering a Rayleigh number from 1,000,000 to 10 to the power 17. The Prandtl number was essentially constant. We similarly did experiments with liquid sodium, which is shown by the blue oval at the bottom left. And the Prandtl number and the Rayleigh number are shown there. I added the work of Goldstein for completeness, which is at the very top. The lines in this diagram indicate simulations of the Boussinesq equations in three-dimensional boxes, covering different ranges of Rayleigh and Prandtl numbers, done with collaborators shown in the violet box to the right bottom. The simulations in the yellow area are the ones that Jörg Schumacher did, which I added because he works very closely with us. I did not add the works of many fine researchers in the US, India, Europe, and China, which I have not fully absorbed, but they don't fall outside this parameter range, so let's leave them out for now. From the parameter range covered, which is 6 orders of magnitude in Prandtl number and about 12 orders of 15 orders of magnitude in Rayleigh number, you might think that I can string together the story of convection, at least for the Rayleigh-Bénard case, but it is a fallacy, as you will see in the next slide. So here I plot common instances of convection in nature. The gray rectangle marks approximately the problem of atmospheric convection. Similarly, the blue symbol marks the case of convection in the Mediterranean Sea, which you can estimate very easily. The green oval in the same vicinity is the Earth's core, outer core, whose convection generates the magnetic field. To the very left on the top is the Earth's mantle, also shown in green, with very high Prandtl number and modest Rayleigh number. And next, we believe I've shown by this flashy red thing to the bottom right, which we believe corresponds to the sun. I use big blobs rather than little symbols because no number is really known that well. By the way, it appears that all these highly important convection problems fall on this diagonal shown by its right line, red line, whose equation I've shown underneath, which may be of some consequence, but I will not consider it further. And of course, if you think of the outer layer of the convection in the sun as a separate problem, that's where it falls, bottom left. But what you see what you see here is the Rayleigh and Prandtl numbers in the systems we know really range over a very large range of the ranges. And in fact, the importance is that you can see the Prandtl number varies from order 10 to 10 power 4. The structure of the temperature field changes very drastically, as I've tried to show here. And because the sun has a relatively low Prandtl number, as I will later on show, this 10 power minus 6 or so, with just an indication here, we are especially interested in the low low Prandtl number regime. Thus, even though, in fact, we covered large ranges of Rayleigh and Prandtl number from a laboratory perspective, I have to approach instances of terrestrial and solar convection with great humility, as is clear when I contract the previous plot onto this diagram. Let's see if I can do that. It's a previous plot. And here is the experiments, and here are the simulations. So you can see that it really covers a very small part of the range that I would really like to understand. And therefore they pale in comparison with the enormity of ranges that nature demands. Nevertheless, that's what I have, and that's what I will be able to say something about on the basis of. So now let's look at the first problem, which is the asymptotic heat transport law. I'm not going to consider the theoretical bounds on this problem due to Doring and his co-authors, but I will consider the precise formula that Malkus and Spiegel gave, which is shown here. Nusselt number goes like Rayleigh to the power 1/3 with a coefficient sitting in front, which is known. There is no Prandtl number in this at all. And Ed Spiegel, who is probably known to you very well, unfortunately died about a year ago, and he was involved in this. And an alternative formula is due to Kraichnan and also Spiegel, which says that the Nusselt number goes like Rayleigh to the power half with a strong Prandtl number dependence as well, although Kraichnan himself had a weaker dependence on the Prandtl number. And this is called the so-called asymptotic state, one imagines for the way it is derived. Spiegel himself pointed out that the difference between the two formulae is large enough that one should really make an effort to find out which is right. And so what does the experiment say? This graph shows the experiment we did with Rayleigh number going from 1 million to 10 to the power 17, about 11 orders of magnitude, not very usual in physics. It's possible to do this, or it was possible to do this, because my colleagues whom I have listed here and I thought about using, as Vinod already mentioned, cryogenic helium. Near the critical point, you can push the helium to give you a wide range of property variations. And therefore, the experiments can cover this broad range. These are now already 20 years old. We repeated them later to confirm this very nice power law, which is close to 1/3 power. Now, there is a slight difference from 1/3, but I don't know this is important or not for us, but we will move on. In spite of this, papers in search of the Kraichnan-Spiegel formula, also asymptotic state, as I said, keep appearing. And one such paper is shown here. And they claimed that, in fact, there is a transition around 10 to the power 13 with an effective coefficient of 0.38, which is slightly different from 1/3, but going in the right direction for the Kraichnan-Spiegel formula. Others claimed this is not right. It was spurious, and in fact, Doring showed that it's not justified by their own data fits. But still, we wanted to look at it again, and this time we did it by numerical simulations. In this paper, in a box like this, it is slender because we could not use even the biggest computer that was available to us could not go much beyond the Rayleigh number of 10 power 15, especially if you used a different type of configuration. And we used as much computing power as anybody has ever used in these problems. Here is what we find. The top three figures show the temperature field at Rayleigh numbers 10 power 9, 10 to the power 11, and 10 to the power 13, and demonstrate the evolution of finer structures as at higher Rayleigh numbers. This figure shows the Nusselt number as a function of Rayleigh number, going from approximately 10 power 5 in Rayleigh number to 10 power 15, 10 orders of magnitude. And if you look at only the red circles, the fit to them is given at the bottom. It has a Rayleigh number dependence of approximately 1/3. with the coefficient that is listed here. You can show this even better by normalizing the Nusselt number by Rayleigh to the power 1/3. You can see that beyond about 10 to the power 10 or so, this is a constant, as one should expect if it is a power law of 1/3. And I think this is fairly conclusive. And I compare this with the Malkus theory, which is Nusselt number with dot coefficient going with Rayleigh to the power 1/3. The comparison says that the coefficient in front also is not so bad. And in comparison, I would show you what the experiment showed. Same power approximately with a slightly different coefficient. So in fact, I would say no ultimate state of thermal convection, at least in this box, is possible. And that's what we find. Now, this is all with the Prandtl number held fixed. So you want to know what the Prandtl number dependence is. So we did a number of numerical studies as well, with Prandtl number varying from a few times 10 power minus 3 to about 10 power 2, if you like. Nusselt number is a function of Prandtl number for keeping for each curve a Rayleigh number fixed. So as the Rayleigh number is small, there's a dependence on this which changes with the Rayleigh number. And in fact, if you plot the exponent, that is slope of these curves, as a function of Rayleigh number, normalized by the onset Rayleigh number, you can see that initially, that is small Rayleigh numbers, there are differences in different apparatus, but towards the end, they all seem to saturate with an exponent which is approximately 0.17. And for someone like me who likes rational numbers, I approximated it like this. Nusselt number is 6 times Rayleigh to the power 1/3, Prandtl number to the power 1/6. This is now the result of a lot of work, and we believe has some consequence. Now, usually people have ignored the dependence on the Prandtl number because it is very small, as it turns out. But the point is that the Prandtl number for the sun is very small, as shown in this slide. I've shown here on the logarithmic scale on the vertical axis, which is logarithm to base 10 of the Prandtl number. On the horizontal axis is the radius from the center of the sun outward. The vertical dashed line, dotted line is where the convection region is supposed to begin. And you can see throughout all this, the Prandtl number is approximately 10 to the power minus 6, except towards the very top of the sun, where none of the calculations make any sense. And usually in fluids that you know, the Prandtl number is of order 1. But why this number is so small in the sun is that the momentum transport and the heat transport are done by 2 disparate mechanisms. The momentum transport is by free electrons and the heat transport is by photons. So that's why it can afford to be very different from unity, and it happens to be very small. Now let's contrast this, relation I obtained from the Rayleigh-Bénard convection with the mixing length theory, which you all know, which I can write like this. Nusselt number is proportional to Rayleigh to the power half, Prandtl to the power half, with the coefficient that can be worked out, which I have, but it's not really important for our purposes. And the ratio is written here. Of course, no matter what the mechanism, the same amount of heat must be transferred. So if I put the ratio to unity, now I have to somehow adjust the Prandtl number and Rayleigh number together to give me the same heat transport. It turns out that if you do it, putting the small Prandtl number of the sun in this formula, we get a convection velocity to be smaller by a factor of about 10 or so, which is one of the issues that I had in the beginning to explain why the velocities are so small. I should not like to take it very quantitatively because there are numbers in front that are really not known so accurately. But let's take it as a qualitative estimate in the right direction and move on. Besides this quantitative result, the convection experiments have shown the following. Low Prandtl number. I have shown here pictures of the flow, both the velocity and the temperature. Look at the top row. Prandtl number varies from 7 on the right to 0.21, which is not really very small. Even in this range, you can see that the scale of the velocity field and the temperature field becomes more and more smaller in size as you go lower and lower in Prandtl number. You can see this quantitatively here on the right picture, Prandtl number on the horizontal axis, and the scales for the velocity field, W, temperature field, theta, and the product of the two, W and theta, which is what transports heat. And you can see as the Prandtl number goes down, the scale in all of them reduces. So this is an important conclusion of the effect of Prandtl number. Even though the scale decreases, the velocity increases. As I've shown on the right picture, the normal velocity is a function of Prandtl number, log coordinates again. The blue line and the symbols are for three-dimensional convection. And for comparison, it's really of no consequence to us, is the red line, which is for the 2D case. Now, what this says is that even though the scale of convection goes down as you go down in Prandtl number, the velocity increases in such a way that the Reynolds number actually goes up as you go down in Prandtl number. And I've shown this in the inset of the left figure, where Reynolds number is plotted as a function of the Prandtl number. As you see, if the Prandtl number goes down, that is, you move to the left of the picture, the Reynolds number goes up. That means turbulence will somehow have to become stronger with decrease in Prandtl number. I will not explain the rest of the figure. There is a fundamental result, which I think all of us know in part, and maybe not all in every part of it. To the left, I remind you what happens to the temperature distribution in Rayleigh-Bénard convection as the Rayleigh number goes up. As the Rayleigh number goes up, the diagram to the left shows that the velocity profiles become more and more straight, more and more vertical in the main part of the apparatus. The drop in the temperature in the bottom and top boundary layers becomes sharper and sharper, and the tendency is therefore to be uniform in the bulk. And if you go to a different Rayleigh number on the right top picture, and you focus on the curve, which is violet in color, forget about the green, you can see that there's a drop in the top boundary layer and the bottom boundary layer. In the bulk of the apparatus, it is essentially vertical, almost like a short, thermal short. And you know all this stuff. But what you probably may not know is that if I fix the Rayleigh number, as I have done in this figure, and vary the Prandtl number, that is, make it smaller and smaller, what you see is that the profile stops being vertical like that in the bulk of the apparatus. And at the very lowest Prandtl number, which is represented by the blue line, you can see that it is almost linear, just like conduction. So there is a heat transport is really now almost by convection, almost by conduction, even though there is a huge amount of turbulence. So if you have followed all that I have said, you will no doubt say something is screwy here, because I already argued that as the Prandtl number decreases, the Reynolds number increases, nominally making the turbulence stronger. Yet the heat transport takes place as if by conduction alone, without caring whatsoever about turbulence. Now, how does this happen? The answer is that even though turbulent energy levels become stronger, they become uncorrelated with the temperature field, which is a theme that I will expand upon later on. Effectively not participating in the heat transport at all. So we expect that for any given Rayleigh number, there always exists a Prandtl number below which turbulence becomes ineffective. Now, since I already argued that the Prandtl number in the sun is very small, the question to ask is whether for the Rayleigh number we know approximately to be the case, what is the situation in the sun? Now, actually, if you calculate the amount of heat transport by conduction alone, near the tachocline, it is very large. It's almost 100% of the heat transport. And only becomes insignificant if you go outwards to approximately, let's say, 50% when you're about 7.75 of the radius. And so on, as you can see from this figure. In fact, this is something that helioseismologists just do not believe, and I have had discussions with some of them. They believe that the convection really begins at 0.7, which I think may well be true, but I'm just saying that the turbulence is relatively weak until actually you go much higher in the height from the tachocline. So I believe this difference is important for the dynamo and such things, but I need considerably more time to convince you of this. So I move on. The truth is that not only is the Prandtl number small in the sun, as the left figure shows, but if you look at thermal diffusivity in the sun, it varies by orders of magnitude from near tachocline 0.7 or so, which is what I've shown in the picture to the right. Thermal diffusivity on the vertical axis, horizontal axis is the solar radius. You can see that it varies by 3 orders of magnitude or so across the convection layer. So the thing is, it's not enough for it to understand the problem. It's not enough for you to just look at the low Prandtl number case, but also see what the effect is of the variation of the thermal diffusivity. So we decided to explore this facet by allowing the thermal diffusivity to vary with temperature in qualitative similarity to the picture that is shown here, but quantitatively not quite right. And the details can be found in this paper that I have just cited at the bottom of the figure. And I highlight only 3 results from here. First of them is that I've shown you the temperature field, slices of the temperature field through the convection apparatus. Going from the bottom of the convection apparatus on the left to the top of the convection apparatus to the right. As one approaches the top wall, which you should think of like outer solar radius because of the diffusivity variations, the larger scales are retained just the same way as in the bottom, but the small scales become stronger. Now you can see that. And if, in fact, you measure the spectrum of the temperature, as I've shown at the bottom left, a wave number on the horizontal axis, which I did not mark, and the energy on the vertical axis, you should take my word for it. These different curves show that as you go from the bottom to the top, the content of the spectrum for higher wave numbers, let's say above 1 or so, actually increase. That is, small scale becomes stronger and stronger. Now, actually, this is true of the thermal gradient as well, which is shown in the picture to the bottom right. Z equal to 0 is the bottom wall and Z equal to H is the top wall. And you can see that the small scale activity just increases. So this is the first point. So whenever you have this thermal diffusivity variations, you should expect small scales to become stronger towards the wall where the diffusivity is small. That is for us, let's say towards the outer surface of the sun. Now, another important factor is that the mean temperature profile is highly asymmetric. So normally, as I've shown, let's say by the green line in the top figure, or by the red line as well for a higher Rayleigh number situation. There's a drop in boundary layer temperature, and then through the bulk of the apparatus, as I have already explained, it's either constant or approaching, nearly constant or approaching constant as the Rayleigh number goes up. Whereas the blue line is for the case of variable diffusivity. The temperature drop in the bottom boundary layer is relatively small, but the temperature boundary layer is large. And you have the temperature in the bulk more or less constant, but not at half, which is the mean value, but much higher than half. And then most of the drop occurs in the bottom boundary layer. Schematically, what this means is what I've shown in these three figures. Figure 1 to the left is what you might expect for symmetric walls, top wall and bottom wall. Or for us, let's say top wall is the outer surface of the sun and the tachocline at the bottom. And if the Prandtl number is very small, I should see the boundary layers thicker, as I've tried to show in figure 2, very schematically. But what the simulations show is that the profile in something like the sun with the variable diffusivity would be like what I've shown in figure 3, very small drop in the bottom boundary layers, very large variation, large drop in the top boundary layer, and variation, as I've shown here, really very far from being symmetric. I've, of course, taken out the adiabatic variations as I should. Now, thirdly, and finally, I have shown here the turbulent diffusivity, which goes back to my question of how effective the turbulence is. For those of you who do not think about thermal diffusivity, turbulent diffusivity, etc., I have defined it for you in the yellow region. What is shown here is Prandtl number on the horizontal axis, and on the vertical axis is the effective diffusivity, which is the ratio of the effective Prandtl number, which is the ratio of the effective viscosity or the turbulent viscosity to effective or turbulent diffusivity. So turbulence somehow is thought here in this problem or in this representation to have the effect of increasing the diffusivities, both for the vorticity and for thermal thing, and the ratio of the two effective ones is really this PRT. Now, this is the one people believe is much more important when you have a turbulent environment. We found that the turbulent Prandtl number varies inversely as the molecular Prandtl number. That is to say, as the Prandtl number, molecular Prandtl number goes down, which is what happens in the sun, very small value, the effective Prandtl number goes up. Now, this is a hard quantity to compute, so there are variations in these data, but a good fit to the data yields the relation that the effective Prandtl number is about 1/10 of 1 over the molecular Prandtl number, as shown in the orange box highlighted at the bottom. The smallest Prandtl number in these simulations is quite small, 10 power minus, almost 10 to the power minus 4. But it is not as small as it in the sun, so where you have to go maybe 2 orders of magnitude smaller. But the relation appears to be simple enough that I can extrapolate it. And if I extrapolate it, what it means is that the effective Prandtl number in the sun's convective region is about 10 to the power 5. That is to say, the effective diffusivity of the temperature is really large by 10 to the power of 5, something like that, effectively. Now, what this means, this means is the following. Suppose at the bottom of the convection region, I have a temperature field and the velocity field represented here by sine waves, fluctuations, let's say. And they are not perfectly correlated, but they are roughly correlated to give you a correlation coefficient of 0.5 or something like that, as is the case in standard turbulence. Since I have shown, let's say, that the effective viscosity is 100,000 times larger than the effective thermal diffusivity, that is, the effective Prandtl number is 10 to the power 5 if I extrapolate it. The velocity fluctuations become smoother very fast as the thing rises to the top. At a later time, the temperature field is unaffected, but the velocity field is already diffused completely or nearly completely. So we thus have the case of temperature structures being advected by a structureless and perhaps a random velocity field. This velocity field is much smaller in magnitude than you might expect from standard phenomenology. In my opinion, this is a very important result and may go some ways in explaining a number of phenomena in the sun. And then the question is, how is the heat transport taking place? And one of them is illustrated in this top figure, which shows schematically thermal plumes persisting throughout the entire region of the convection. This idea is not mine. I have shown here at least some of the people who have been involved in this, although their details are very different from what I have just mentioned. In summary, what I have attempted to show is some selected results of the panoramic view of convection for the parameter ranges that might apply to a range of important physical problems. And since sun is of interest to you, I have mainly focused on the sun, but we can discuss others like the earth, which I will not do here. I also do not discuss effects of aspect ratio and rotation, which is quite important, etc. There are competing influences of the Prandtl number on rotation. And of course, said nothing about the magnetic field, which is of enormous interest. I will not say any of this in view of the time, but I want to return to Vainu Bappu, as I said I would. In 1982, when he was discussing the connection between the sun and stars as an important problem in astrophysics, here is what he said. This is the last lecture he delivered in Ahmedabad as a part of the lecture he gave in a special lecture. And here is what he said. It's always been a statement which every astrophysics teacher imparts to his students that the sun is a typical star, and therefore it is essential to use the sun as a testing ground for all kinds of theories. Unfortunately, this is basically a theoretically induced statement, which apparently seldom holds in practice because in these days of specialization, we have reached a stage where there are so many things that we have been able to see only in the sun, which we would like to see in the stars. And there's so many things in the stars which we would like to see and verify in the sun. Hence, at this moment, establishing the close interplay between the sun and the stars is a task that we set upon, and this interplay between the sun and stars is really what I hope I would be able to demonstrate in the course of the lecture, a series of lectures. Now, I think he would have been delighted to witness the progress made in this connection, the field of heliophysics, its connection to other stars, and many exoplanets being discovered makes this a very exciting time, especially for someone like me. By the way, Pisharotti, who was the director of PRL, he wrote a preface to these lectures, and this is how he described Vainu Bappu. If you know Sanskrit, you can read the top line. Otherwise, read just the bottom line. Only erudite and precise speech properly adorns a person, and that's how he characterized Vainu Bappu. So here is where we are. And I think he would have been very happy with the progress that we've been able to make, but not so sure about the still remaining problems in the sun itself. So I close my talk with many thanks again for this honor and an acknowledgement of the people from whom I've learned a lot in this problem, aside from the ones I have named in the talk itself. And thank you for joining. And again, my gratitude. Bye.
Okay. Thank you, Professor Sreenivasan.
I stop sharing now, if you want.
Could we invite some questions from the audience? Will you be able to?
Yes, I will be very pleased to do that.
Okay, so there are some raised hands. Let me go with the order we saw the raised hands. So Dibyendu, can you unmute and ask your question?
Yeah, thank you, Rajaguru. That was a wonderful talk, Professor Sreenivasan. I really enjoyed it. This is Dibyendu Nandi from ISER, Kolkata. So you talked about the influence.
I know where you are.
Well, thank you. So you talked about the influence of Prandtl number on convection and turbulence near the base of the sun's convection zone, yes. And where the tachocline is situated. Now, this is a very interesting region, especially for us dynamo theorists, because yes. We believe that this is where large-scale organized toroidal flux tubes that form sunspots are situated. Yes. Although there is some debate on this, it is also believed that these flux tubes are probably at least equipartition, if not superequipartition fields, which might quench turbulent convection in this region. So what effect do you think this might have, if any, on the paradigm that you discussed?
Yeah, I always wondered about the same question. You have to have some special case of turbulence near the tachocline for this magnetic field to survive intact, for the flux tubes to form the way they're supposed to form. And I think the lack of the effectiveness of turbulence is very strongly supportive of what is presumed to happen. I always wondered if you have really strong turbulence that tears apart these flux lines, how in the world does the dynamo action take place? I am tempted to say that this is completely consistent with the kind of things you've been asking yourself and a number of others.
Exactly. I mean, that was exactly my thought. So I was actually pretty happy to look at your paradigm.
Yeah, well, thank you. Yeah.
Thanks.
Okay, so the next question is by Vidya Karat. Go ahead, unmute and ask your question.
Yeah,
hi there.
Thank you, Professor Sreenivasan. So you can again recall me, I guess. So I'm in ITVHU. So I like your this idea that you emphasize the large turbulent Prandtl number. Probably this is also true in the sun, and you said that there is already a paper. So I also did some simulation with Mark Mies and Uto Becky. There we tried to capture the consequence of large turbulent Prandtl number. So one problem that, so one good thing is that it actually reduced the convective velocity in the sun, which is the big problem now. But then like when you have large effective Prandtl number, it produces very efficient plume, and those plume actually transport the angular momentum inward, and it actually I mean, it actually made the differential rotation anti-solar. Okay, so by transporting the angular momentum by room. Okay, so I can share this paper in details and I discuss this. So my question is, like, I mean, you showed some data where you showed this turbulent Prandtl number as a function of the molecular Prandtl number. So my question is how this turbulent Prandtl number is measured in those plot.
Yeah, this is measured by invoking the so-called K-epsilon model, where you deduce the kinetic energy, turbulent dissipation, which are related by diffusivity and analogous quantity for the temperature field. So I can send this to you. By the way, I could have written in my last slide where I said Remfel, Mish, and others. I could have included even name, which I just did not. The point is, you are worried about the anti-solar differential rotation. I believe that that is probably not going to happen because even though the molecular Prandtl number, you just remember what the effect of the effective Prandtl number being very high is. It means that the thermal field uh, um, simply does not diffuse, whereas the vorticity field diffuses very fast. So you have these thermal plumes descending, but not the vorticity field itself, not in the form of plumes. So it's the vorticity field is sort of background, more or less random in my view, not very well organized. And therefore, the concern you have about the anti-solar rotation, in my mind, is not very relevant, but we should discuss this at some point. I appreciate the work you have done in this connection. Thank you.
Okay, thank you.
So the next question is by Arnab. Arnab, go ahead and ask your question.
Okay.
Hi, Arnab.
So
Greetings.
hello, Srini. Nice meeting you at least virtually after a long time. Probably last time we met at the conference for your 70th birthday.
Yes.
Anyway,
Embarrassing though it is. Yeah.
Yes. Anyway, so you are mainly comparing the results of Rayleigh-Bénard convection and laboratory experiments with the convection deep in the sun's convection zone and near the tachocline. And I think there are lots of uncertainties either from theoretical consideration or from helioseismology observation, but what are the typical time scales and what are the velocities and things like that. On the other hand, in the top layer, in the granular convection, we know all these things, what are the various scales, length scales and velocities and things like that. And I think at the beginning of your talk, you made some comments about that this region is difficult to compare. But somehow I think this photograph of solar granulation looks so much like a photograph of Bénard cells, like Bénard's original photographs, only more irregular. So I always thought that at some level it should be possible to compare this granulation, granular convection with some Rayleigh-Bénard convection. So what is your response to that?
So my view is regular Rayleigh-Bénard will simply not do because the properties of the fluid there are simply not known. There are only partially ionized gases there, all of that. But there are people who have really considered all of these things carefully, like Nordland and others. And my thinking is that if you think of the outer skin of convection and regard that as almost an independent convection problem, which is connected to the deep convection through some simple parameters, it's probably much better understood than the rest of the convection problem. And the point you made about the granules and all the wonderful things you have done and written in your also terrific book, which I wrote to you about a long time ago. I think those are really reasonably well understood in my opinion. I have read much of the literature, but I have not really worked on that part myself, only because I don't even know the state of the gas. Um, and I don't know how to do any better than what other people have already done. But I think that's the part that is open to us for direct observations and therefore amenable to direct comparisons. And this, in my view, has been done pretty well by a number of people.
Okay. Thank you, Srini. Is there any other question from the
Rajguru, may I?
Yeah, go ahead, and probably yours will be the last question and you can.
Yes. I just have a very general thought, I would say. Srini, with your vast experience in turbulence, would you say that turbulence tends to enhance the transport or diffusion parameters which are classically low and vice versa?
Yeah, I think that is always the case, but I am just making the distinction that because the Prandtl number is very small, its effects are such that it enhances one type of diffusivity and not the other. And that is the main point I am making. And in that sense, turbulence is very effective in some ways and not so effective in others. And that I think in my own mind makes a lot of sense in terms of the dynamo theory and as others have pointed out here. The ineffectiveness in some sense of turbulence in the bottom part of the convection region. So that's my main message, actually. Thank you for asking the question so I could repeat it.
Thank you.
And thanks again for your enormously generous introduction.
I am not done yet.
Yeah.
Okay, all right.
Go ahead.
Okay, so Rajguru, what's next?
Yeah, so you can go ahead, say the vote of thanks and then.
Okay, so another something more, Srini.
Okay, all right.
So this is vote of thanks. Okay, let me see. Yeah. So in an interview given some time back, Professor Sreenivasan recalled that in his early childhood, Adi Shankaracharya appeared in his dream and said, I quote, I am wasting my time and look at how much Vivekananda accomplished before he died at the age of 39, unquote. I am sure Shankaracharya would appear again in your dream and say, well done, my boy. Or maybe he has already appeared?
No, it was Vidyaranya that appeared in my dream and said, I'm wasting my time.
Okay.
And he hasn't reappeared to tell me anything differently.
Okay. So we hope it will happen soon. And we thank Professor Sreenivasan for his wonderful lecture. Let us give him a big hand. Thank you, Professor Annapurni, for conceiving and organizing this splendid event. Thank you, Professor Rajguru, for planning and doing the needful. Thank you, audience, and thank you, Vinod Krishnan.
Thank you. Thank you all.
Thank you, Srini. So I think we will close this session and we have the next session of the conference in about 45 minutes, less than 45 minutes at 8:30.